There's a star at the center of our solar system that has been burning for 4.5 billion years. Every second, it converts 600 million tons of hydrogen into helium, releasing energy so vast that in a single hour, it delivers more power to Earth than our entire civilization consumes in a year. We use almost none of it. We scratch at the surface of our own little rock, burning ancient carbon, splitting atoms, catching fragments of wind, while a fusion reactor of incomprehensible scale blazes quietly at our doorstep, ignored, untapped, and patient. Today, we're going to talk about what happens when a civilization finally decides to stop ignoring it. We are going to examine the most ambitious engineering concept in the history of human thought, the Dyson Swarm, a structure, or rather a constellation of structures, that would eventually envelop our entire sun, capturing its total energy output and redirecting it toward the purposes of a civilization that has outgrown its planet. And we are going to ask with complete seriousness whether building would be the greatest achievement our species is capable of, or the last decision we would ever make as a free civilization. This is not science fiction. The physics are real. The engineering pathways, while staggering in scale, do not violate a single known law of nature. Several serious scientific papers have traced credible routes from where we are today to a partially constructed swarm within centuries, and completed one within millennia. The question has never really been whether it's possible. The question is whether it's wise. Because wrapped inside the most elegant solution to our energy problem is a paradox that grows darker the longer you look at it. A paradox of irreversibility, of control, of what it means for one species, or one faction of one species, to hold the power of a star in its hands. That is where we are going tonight. And it begins, as so many of humanity's most consequential stories do, with a single, deceptively simple question: how much energy is enough? To understand why a Dyson swarm exists as a concept at all, you have to understand a wall that every sufficiently advanced civilization must eventually hit. Not a political wall, not a social one, a physical one, a ceiling written into the laws of thermodynamics itself. Right now, humanity consumes roughly 600 exajoules of energy per year. That number sounds abstract until you try to hold it against something human. Imagine every car ever manufactured, every power plant ever built, every furnace, every engine, every data center, every light bulb that has ever been switched on across the entire span of recorded human civilization, all of it running simultaneously, continuously, for a full year. That is approximately the scale of what we use. And that number is not staying still. It doubles roughly every century, sometimes faster. The more complex our civilization becomes, the more energy it demands, not linearly, but exponentially. Intelligence, it turns out, is extraordinarily hungry. The Russian astrophysicist Nikolai Kardashev understood this in 1964, when he proposed a framework so clean and so brutally honest that it has never really been improved upon. He suggested that any civilization, anywhere in the universe, could be categorized by a single metric: how much energy it controls. Not how sophisticated its art is, not how complex its philosophy, not how advanced its medicine. Energy, because energy is the substrate beneath everything else. You cannot run a hospital without power. You cannot transmit information without power. You cannot sustain 8 billion people, let alone 80 billion, without power. Energy is not merely a resource. It is a currency of existence itself. Kardashev defined 3 types. A Type 1 civilization controls all the energy available on its home planet, roughly 10 to the 16th watts. A Type 2 controls all the energy output of its parent star, roughly 4 times 10 to the 26 watts. A Type 3 controls the energy of an entire galaxy. The gaps between these levels are not incremental. They are not even dramatic. They are almost theologically vast. The difference between Type 1 and Type 2 is the same order of magnitude as the difference between a single candle flame and every nuclear weapon ever built, detonated simultaneously. We are not yet Type 1. We hover somewhere around 0.7 on Kardashev's scale, advanced enough to devastate our own biosphere. not yet advanced enough to power our civilization from the sky above us. The ceiling is coming, not in decades, probably not in centuries, but in the time frame that any civilization serious about its own future must plan for. The ceiling is real and it is absolute. You cannot run a post-scarcity interplanetary civilization on fossil fuels. You cannot run a computational infrastructure vast enough to simulate weather systems, model drug interactions for 10 billion people, and coordinate global logistics on wind and solar panels scattered across a single continent. At some point, the arithmetic forces a reckoning, and the arithmetic always points in the same direction, upward, toward the sun. This is why Freeman Dyson matters. Freeman Dyson was not the kind of scientist who made headlines. He did not have the theatrical flair of Carl Sagan or the cultural ubiquity of Stephen Hawking. He was a theoretical physicist who worked quietly at the Institute for Advanced Study in Princeton for most of his career, a man whose intellectual range was so enormous that he sometimes seemed to be operating in a different cognitive register than his peers. He worked on quantum electrodynamics alongside Richard Feynman. He designed a spaceship intended to be propelled by nuclear explosions, a project called Orion, one of the most audacious engineering proposals in history. He thought seriously about the far future of life in the universe at a time when doing so was considered, at best, whimsical. In 1960, he published a paper in the journal Science. It was less than 2 pages long. Its title was almost aggressively understated: Search for Artificial Stellar Sources of Infrared Radiation. And in those 2 pages, Freeman Dyson changed the way humanity thinks about the relationship between intelligence and stars. His argument was not, as popular culture would later misrepresent it, a blueprint for building a giant hollow shell around the sun. That image, the perfect geometric sphere, smooth as a billiard ball, wrapping a star like a Christmas ornament, is a misconception so persistent it has become almost mythological. Dyson himself found it frustrating. What he actually proposed was far more subtle and in many ways far more interesting. He began with a premise that is almost impossible to argue with. If intelligent life exists elsewhere in the galaxy, and Dyson thought it likely that it did, then some of those civilizations will be older than ours, perhaps millions of years older, perhaps hundreds of millions. And any civilization that has existed for that long, that has continued to grow in complexity and energy demand, will have eventually confronted the same ceiling we are approaching. They will have needed more energy than their planet could provide. And the obvious, perhaps inevitable, solution is the same one our own physics points toward: collect the light of the star. What Dyson proposed was that a sufficiently advanced civilization would, over a long period of time, disassemble some portion of the solid material in their solar system, planets, moons, asteroids, and use that material to construct a vast collection of orbiting structures around their sun. Not a solid shell, which would be mechanically impossible and gravitationally unstable, but a swarm, a cloud of millions, eventually billions, of individual platforms, collectors, habitats, and mirrors, each one independent, each one in its own calculated orbit. Together, they would intercept an increasing fraction of the star's total output, converting into usable energy and re-radiating the waste heat as infrared radiation. The key insight, the one that makes this astrophysically relevant rather than merely speculative, is that from a distance, a solar system undergoing this kind of construction would look different. It would grow dimmer in visible light as more of the star's output was captured, and it would grow brighter in infrared, because all that captured energy eventually has to go somewhere, and waste heat radiates at lower temperatures. A civilization halfway through building a Dyson Swarm would be, from light years away, a star that was slowly going dark while glowing in wavelengths the human eye cannot see. This is what Dyson was really proposing. Not an engineering manual, but a detection strategy, a way of identifying other intelligences across the cosmos by the thermodynamic fingerprint of their ambition. It is worth sitting with that image for a moment, because it is one of the most quietly profound ideas in all of modern science. The thought that scattered somewhere in the infrared catalogs of our telescopes, there might already be the signatures of civilizations that made the decision we are only now beginning to contemplate. Civilizations that looked at their star, did the arithmetic, and began, that we might be, without knowing it, already observing the consequences of choices made by minds we will never meet. Around suns are thousands of light years away. But let us bring this back to our own star, our own solar system, our own species standing at its particular moment on the Kardashev ladder. Because the swarm Dyson described is not merely a philosophical abstraction. It has been examined seriously by physicists, engineers, and astrobiologists, not as a project for next century, but as a framework for thinking rigorously about what the very long-term future of a technological civilization actually looks like. So what would a Dyson swarm around our sun actually consist of? The simplest and most credible near-term component is also the most elegant: individual solar power satellites. Not the rooftop panels you might imagine, but enormous thin film collectors, perhaps kilometers across and only micrometers thick, orbiting the sun at various distances and converting sunlight directly into electricity or microwave radiation. That radiation would then be beamed to receiving stations on Earth, on other planets, on orbital habitats. With extraordinary efficiency, this is not exotic physics. Microwave power transmission has been demonstrated on Earth. The engineering challenge is one of scale, not principle, as the swarm grows. And this growth is imagined over timescales of decades to centuries for early phases, millennia for full development. It becomes something far more complex than a collection of solar panels. Habitats, research platforms, manufacturing facilities running on essentially unlimited power, communication arrays of sensitivity we can barely imagine from where we stand today. The swarm, at full development, is not merely a power grid. It is a civilization, a distributed, solar-powered civilization that has effectively moved its center of mass off the surface of any individual planet and into space itself. The physicist Stuart Armstrong at Oxford's Future of Humanity Institute, along with the astronomer Anders Sandberg, published detailed analyses in the early 2010s that traced a plausible engineering pathway from our current state to an early-stage Dyson swarm. Their estimates suggested that a civilization with access to self-replicating robotic manufacturing, machines that can construct copies of themselves from raw materials, could, in principle, bootstrap a significant partial swarm within decades of beginning construction in earnest. The key word is self-replication, because the challenge of a Dyson swarm is not the physics of the individual collector. It is the sheer number required to make a meaningful dent in the sun's total output. You are talking about millions of large structures. No human-operated factory could produce them fast enough, but a factory that builds copies of itself, each copy building more copies, operating on the abundant solar energy already available in space, that changes the arithmetic entirely. This is where the vision becomes not merely grand, but almost vertiginous. Because once you introduce self-replication into the picture, the growth curve of the swarm stops being linear and becomes exponential. And exponential growth, when the inputs are essentially unlimited, does not stay manageable for long. There's a concept in computer science called a von Neumann probe, named after the mathematician John von Neumann, who first described the theoretical possibility of self-replicating machines in the 1940s. A von Neumann probe is a machine that can travel to a new location, harvest local resources, build a copy of itself, and send that copy onward. In the context of interstellar exploration, this concept is often invoked to explain how a single civilization could eventually populate an entire galaxy with its emissaries, simply by waiting long enough for the exponential cascade to unfold. The same logic applies here. Turn inward, not a probe sent to other stars, but a replicator sent to the asteroid belt, to the moons of Jupiter, to the surface of Mercury, building, copying, until the infrastructure of a Dyson swarm begins to take shape not over geological time, but over human time. Not thousands of years, perhaps hundreds. Freeman Dyson himself never claimed this would be easy. He never claimed it would be without consequence. His 1960 paper was, at its core, a thought experiment, a formal invitation to take the long view of what technological civilizations actually do when they run up against their resource limits. But what the subsequent 60 years of analysis have revealed is that the thought experiment has teeth. The engineering is plausible. The physics is sound. The pathway exists. And here is where the story begins to shift. Because every pathway has a destination. And when you trace this particular pathway to its end, when you follow the logic of the swarm not just through its first optimistic phases of construction, but through its full development and implications, the destination begins to look less like a triumph and more like a trap, not because the engineering fails, but precisely because it succeeds. The swarm will require raw materials on a scale that dwarfs anything in human experience. Billions of large structures cannot be built from nothing. They must be built from something, and that something must come from somewhere within our solar system. We are talking about the systematic disassembly of worlds. Entire planets reduced to feedstock, moons consumed, asteroids stripped clean, and the consequences of that planetary surgery, the gravitational, ecological, and civilizational consequences, are something we have barely begun to reckon with. The first candidate by almost every serious engineering proposal is Mercury. And what happens to Mercury and to the solar system when we begin to take it apart is a story that changes everything about how we think about this project. The first candidate by almost every serious engineering proposal is Mercury. It is not a sentimental choice. Mercury has no atmosphere worth mentioning, no liquid water, no biosphere, no moon of its own to complicate the orbital dynamics of its removal. It sits closer to the sun than any other planet, which means that material launched from its surface requires less energy to reach the inner solar system's prime real estate. The orbital bands where sunlight is strongest and construction is most efficient. It is, from a purely engineering perspective, an almost ideal sacrifice, a world chosen not for what it is, but for what it can become. Mercury's mass is approximately 3.3 times 10 to the 23rd kilograms. That number means very little in isolation, so let us try to hold it against something human. If you were to take every structure humanity has ever built, every skyscraper, every bridge, every dam, every road, every building on every continent, and weigh it all together, the total mass of human construction across our entire recorded history would be vanishingly small compared to Mercury. Not smaller by half, not smaller by a factor 10, smaller by a factor of roughly 10 billion. Mercury is not a rock, it is a world, and the proposal on the table, stated plainly, is to take it apart. The most frequently discussed method involves a combination of mass drivers and solar-powered mining operations. A mass driver is essentially a very long electromagnetic railgun built along the surface of a planet or asteroid, capable of accelerating material to orbital or escape velocity without the need for chemical rockets. You mine the surface, you process the ore, you load the feedstock into the driver, and you launch it into space where automated factories wait to receive it and fabricate the components of the swarm. Build enough mass drivers, power them with the abundant sunlight at Mercury's orbit, and the throughput scales. Slowly at first, then faster as more infrastructure is built from the material already processed, until the operation achieves a kind of autonomous momentum, a planetary-scale machine that feeds on a world to build a civilization. The timeline, under optimistic but not unreasonable assumptions, runs something like this. Early robotic missions established the first mining infrastructure in the first decades of project. Self-replicating manufacturing systems, once deployed, begin doubling their own capacity at regular intervals. Within a century, the operation has grown large enough to be visible from Earth with the naked eye, not as a structure, but as a dimming, a slight, measurable reduction in Mercury's reflected light as its surface is consumed. Within 5 centuries, a significant fraction of Mercury's mass has been converted into orbital infrastructure. The swarm, at this stage, intercepts perhaps 1% of the sun's total output. That sounds modest until you do the arithmetic. 1% of the sun's output is still approximately 10,000 times the total energy consumption of our current global civilization, and the process would be far from finished. There is a phase in the development of any large engineering project that engineers sometimes call the commitment threshold. It is the point at which the cost of stopping exceeds the cost of continuing. The point at which so much has already been invested, so much infrastructure already deployed, so many systems already interdependent, that halting the project would itself constitute a catastrophe. A half-built dam is more dangerous than no dam at all. A half-laid railway line strands communities on both ends. The commitment threshold is the moment a project stops being a choice and becomes a condition. For a Dyson Swarm, this threshold arrives earlier than most people intuit, and it arrives in a way that is not merely economic but gravitational. Mercury, as it stands today, plays a quiet but non-trivial role in the gravitational choreography of the inner solar system. Its mass influences in small but measurable ways the orbital resonances between planets. The precession of Earth's own orbit has a detectable Mercurian component. These effects are small over human timescales. Over millions of years, they matter considerably. Remove Mercury, not all at once, but progressively, over centuries, and you are altering the gravitational architecture of the solar system in ways that are, at our current level of modeling, not fully predictable at long time scales, not dramatically, not cataclysmically on any near-term horizon, but irreversibly. Once a planet's mass has been dispersed into millions of orbiting collectors, it cannot be reconstituted. The solar system that existed before the project began will never exist again. This is the first layer of the dilemma, and it is worth sitting with carefully. We are not talking about environmental impact in the sense that we usually mean it, the degradation of an ecosystem, the pollution of a watershed. We are talking about the permanent alteration of a planetary system, a change measured not in parts per million, but in the mass of worlds. And unlike almost every other large-scale project in human history, this one has no undue function. There is no treaty you can sign, no technology you can deploy, no act of collective will that reconstitutes a disassembled planet. The commitment, once made beyond a certain scale, is forever. The physicist and science writer David Brin has written about what he calls the irreversibility problem in megastructure construction. The recognition that projects of this magnitude do not merely reshape the physical environment, but reshape the option space available to all future generations. Every ton of Mercury converted into orbital infrastructure is a ton of Mercury that future human beings or future inhabitants of this solar system, whatever form they take, will never have access to in its original configuration. We are not spending a resource. We are eliminating a category of resource permanently, for all time, in exchange for energy now. And we are doing so at a scale and a pace that our current civilization is only beginning to be able to reason about. There is a philosophical tradition in environmental ethics that speaks of obligations to future generations. The idea that we do not inherit the earth from our ancestors, but borrow from our descendants. That framework was developed with rivers and forests in mind. It applies with terrifying force to planets. But let us suppose, for the sake of following the logic honestly, that we make peace with this irreversibility. Let us suppose that the civilizational energy calculus is compelling enough, that the need is real enough, the benefits distributed broadly enough, that humanity collectively decides a trade is worth making. Mercury is the price of our future, and we are willing to pay it. The engineering then proceeds. The swarm grows. Decades pass, then centuries. The fraction of solar energy intercepted climbs from fractions of a percent to single digits to tens of percent. The infrastructure becomes, across its full expanse, the most complex and most powerful structure ever built by human hands, or by the robotic hands we will have delegated construction to. Billions of individual platforms in intricately calculated orbits, each one a node in a power grid that dwarfs anything in our current experience by orders of magnitude that strain language. And here, at this stage of the thought experiment, a second problem emerges, one that is in many ways more dangerous than the first, because it is not a problem of physics or engineering. It is a problem of power, in the older and more troubling sense of the word. Who controls the swarm? This question sounds almost naive in the context of a discussion this cosmic in scope. It sounds like the kind of bureaucratic concern that surely pales beside the grandeur of stellar engineering. But follow it honestly, and it becomes the darkest thread in the entire project. Because a Dyson Swarm is not merely an energy source. It is the energy source, the total or near total output of our star, captured and redirected by infrastructure that someone or some group of someones must operate and maintain and govern. Whoever controls the flow of that energy controls, in the most literal possible sense, the ability of every other entity in the solar system to survive. Think about what that means. Think about the history of human civilizations organized around single, critical, irreplaceable resources. Water in the ancient Near East, where the first cities rose along rivers that could be dammed, diverted, withheld. Oil in the 20th century, where control of petroleum deposits determined the trajectory of wars, economies, and political systems across the entire planet. In every case, the concentration control over a critical resource produced the same outcome. The entity that controlled the resource accumulated power that was qualitatively different from any other form of power. Not just influential, not just wealthy, existentially dominant, capable of determining whether other entities lived or died, not through military force alone, but simply by managing the flow of something everyone needed. Now scale that dynamic to a star. A civilization that has transitioned its energy infrastructure to a Dyson Swarm has, by definition, made itself dependent on that swarm for everything. Not some things, everything. Heat, light, computation, agriculture, manufacturing, transportation, communication. All of it flows from the collected output of the sun, redirected to the infrastructure of the swarm. If that infrastructure is governed well, distributed equitably, maintained as a commons, then perhaps the civilization flourishes in ways we can barely imagine from where we stand. But if it is not, if the swarm, or even a significant portion of it, falls under control of a single entity, a government, a corporation, an artificial intelligence, a faction of any description, then that entity possesses something no conqueror in human history has ever possessed: the ability to turn off the sun. Not literally, of course. The sun continues to burn regardless. But from the perspective of every habitat, every colony, every agricultural system, every computational infrastructure depends on the swarm's output. A deliberate interruption of power delivery is functionally indistinguishable from extinguishing the star. You do not need to destroy a civilization's weapons to defeat it. You only need to cut its power. The historian Yuval Noah Harari has argued that the defining feature of the most dangerous technologies in human history is not their destructive capacity, but their asymmetry, the degree to which they concentrate effective power in fewer and fewer hands, while simultaneously increasing dependency of everyone else. Nuclear weapons were dangerous partly because of their destructive yield, but also because only certain states could build and maintain them, creating a permanent stratification of global power that has never fully dissolved. The internet was supposed to democratize information, and in many respects did. But it also produced a handful of platforms that now mediate the information diet of billions of people, with consequences we are still struggling to understand. A Dyson Swarm represents asymmetry at a scale that makes nuclear monopoly look quaint. The infrastructure required to build and maintain it is so vast, so technically complex, so dependent on sustained coordinated effort across centuries, that it is almost impossible to imagine it emerging from a genuinely distributed, democratic process. It will require institutional continuity across timescales that dwarf any government in human history. The Roman Empire lasted roughly 5 centuries in the West, longer in the East. The construction of a full Dyson Swarm, under even optimistic timelines, runs a millennia. No democracy, no corporation, no dynasty has ever maintained coherent institutional identity across that span of time. Something would have to govern this project. And whatever governs a project for 1,000 years does not emerge from that millennium looking like what it was when it began. What it looks like instead is something we do not yet have adequate language for. An entity of such accumulated institutional power, such infrastructural control, such dependency relationships with every other civilizational node, that the categories we currently use, government, corporation, empire, seem almost childishly inadequate. We are describing something closer to a geological force, something that, like the swarm itself, has become part of the permanent background condition of existence in this solar system. And whether that entity is benevolent or malevolent becomes, at that scale, almost beside the point, because an entity that controls the total energy output of a star does not need to be malevolent to be dangerous. It only needs to be fallible, only needs to make mistakes, only needs to face pressures, internal contradictions, cascading failures of the kind that every complex institution eventually faces. And the consequences of those failures at this scale are not recoverable in any ordinary sense. But even the governance catastrophe, the energy monopoly, the irreversible transformation of the solar system, even all of this might be manageable if the stakes were only civilizational, if the risk were merely to the political and economic organization of humanity. Because civilizations have collapsed before. Empires have fallen. Resources have been concentrated and then redistributed through revolution, through collapse, through the slow erosion of time. Human beings have demonstrated, across our long and difficult history, a remarkable capacity to rebuild. What tips the dilemma from the merely catastrophic into the genuinely existential is something that comes from outside our solar system entirely. Something quiet and cold and deeply unsettling. It comes from looking at the sky and asking a question that Freeman Dyson built into the foundations of his 1960 paper, a question that has grown only more insistent in the decades since. If a Dyson swarm is a logical endpoint of any sufficiently advanced technological civilization, if the physics are universal, if the energy mathematics apply to any intelligence anywhere in the cosmos, then the universe should be by now full of them. We should be surrounded by the infrared signatures of 1,000 civilizations, 1,000,000 civilizations, each one a star slowly going dark in visible light, blazing in the thermal wavelengths, the unmistakable thermodynamic fingerprint of minds that made the choice. Our telescopes have been looking. For decades now, they have been looking. And what they have found, or more precisely, what they have conspicuously not found, is a silence so complete, so uniform, so total, that it constitutes one of the most troubling data points in the entire history of science. And what they have found, or more precisely, what they have conspicuously not found, is a silence so complete, so uniform, so total, that it constitutes one of the most troubling data points in the entire history of science. The universe is 13.8 billion years old. Our sun is 4.5 billion years old, which means that when formed, the universe had already been running for more than 9 billion years. Stars older than ours have existed long enough to have harbored planets, evolved complex chemistry, produce intelligent life, and given that lifetime enough to not merely contemplate a Dyson swarm, but to build one, complete it, and expand outward into the galaxy itself. All before our own solar system had even coalesced from its natal cloud of gas and dust. If technological civilizations arise with any regularity across the cosmos, some of them had a 9 billion year head start on us. And 9 billion years, at the pace of exponential technological growth, is not a slight advantage. It is an almost incomprehensible chasm. So where are they? This is the Fermi Paradox, posed in its original form by the physicist Enrico Fermi during a casual lunch conversation in 1950, and has never been satisfactorily answered. Fermi's question was simple. Given the age and size of the universe, given the apparent abundance of stars and planets, given the seemingly inevitable tendency of matter to organize itself into increasing complexity under the right conditions, where is everybody? Where are the signals, the probes, the megastructures, the unmistakable signatures of minds that got there before us? In the context of Dyson Swarm specifically, the silence takes on a particular sharpness, because unlike radio signals, which fade with distance and require us to be pointing our receivers in the right direction at the right time, the infrared signature of a Dyson Swarm is omnidirectional and persistent. It does not require us to be listening. It does not require the civilization to be broadcasting. It is simply a consequence of thermodynamics. Waste heat radiates in all directions, continuously, for as long as the swarm operates. An all-sky infrared survey should, if Dyson swarms are common, reveal them the way a thermal camera reveals warm bodies in a dark room, automatically, passively, inevitably. In 2015, a team of researchers led by Jason Wright at Penn State conducted exactly this kind of survey, searching through data from the WISE Infrared Space Telescope for galaxies that showed anomalous mid-infrared excess, the signature you expect from a civilization that had built Dyson swarms around a significant fraction of its stars. They examined roughly 100,000 galaxies. They found a handful of candidates showing mild excess emission, less than 1% of the sample, and even those candidates have not been definitively attributed to technological activity. The overwhelming majority of the universe's galaxies show no sign whatsoever of large-scale stellar energy harvesting. No galaxy blazing anomalously in the infrared. No obvious Kardashev Type 3 civilization redecorating the energy budget of an entire stellar population. The universe, at the scales where Dyson swarms should be unmissable, appears to contain none. There are, broadly speaking, two categories of explanation for this absence, and they point in very different directions. The first category is reassuring, at least on the surface. Perhaps Dyson swarms are simply not what advanced civilizations build. Perhaps there are more efficient, less detectable ways to harvest stellar energy, technologies so far beyond our current physics that they leave no thermodynamic footprint we can recognize. Perhaps advanced civilizations trend toward miniaturization rather than megastructure construction, running their entire computational and civilizational infrastructure on quantum systems of vanishing physical size, sipping energy rather than devouring it, invisible to our surveys not because they failed, but because they succeeded beyond our ability to detect success. This hypothesis has a name in the literature, the transcension hypothesis, developed by the futurist John Smart, which proposes that the long-term trajectory of technological development is inward rather than outward, toward greater density, greater efficiency, greater complexity in smaller and smaller volumes, rather than toward the stellar-scale expansion we naively project from our current vantage point. If this is correct, the silence is not alarming. It simply means we are looking for the wrong signatures. The advanced civilizations are there, all around us, but they have made themselves thermodynamically quiet in ways we do not yet understand. The universe is full of intelligence. We simply cannot see it yet. The second category of explanation is considerably less comfortable. Perhaps civilizations do build Dyson swarms. Perhaps the logic is as compelling to them as it appears to us, and the engineering pathway is as accessible and the energy mathematics are as persuasive. Perhaps they begin construction with the same optimism we bring to the thought experiment. And perhaps somewhere in the process, in the governance crisis, in the irreversibility cascade, in some consequence of stellar-scale engineering that we have not yet had the sophistication to anticipate, they stop, not because they chose to stop, but because something stopped them. This is one version of what the astrobiologist David Grinspoon and others have called a great filter, the hypothesis that somewhere between simple chemistry and galaxy-spanning civilization, there exists one or more developmental hurdles so difficult, so dangerous, so statistically lethal to technological species, that almost none survive them. The question that haunts every serious engagement with the Fermi Paradox is not merely whether the great filter exists, it is where it sits on the timeline, behind us or ahead. If the filter is behind us, if the hard part was abiogenesis or the evolution of eukaryotic cells or the development of language or some other improbable step that humanity has already navigated, then the silence makes sense and our future is open. We are the rare ones, the lucky ones. We made it through. If the filter is ahead of us, if the thing that destroys technological civilizations is something that only becomes accessible after a certain level of capability is reached, then the silence is not reassuring at all. It is a warning. It is the universe showing us, in the language of absence, what happens to species that reach the next level. And a Dyson Swarm is, by definition, a next-level technology. Let us look with clear eyes at the specific candidates the universe has offered us, the anomalies, the near misses, the objects that briefly made serious astronomers wonder whether they were looking at the product of alien engineering. KIC 846-2852. It is a star in the constellation Cygnus, approximately 1,400 light-years from Earth, and when the Kepler Space Telescope began monitoring it for the characteristic dimming signatures of transiting planets, it found something that did not fit any simple natural explanation. The star dimmed irregularly, asymmetrically, by amounts ranging from less than 1% to more than 20%, far more than any known planet could produce, and in patterns that seemed almost willfully non-periodic. In 2015, the astronomer Tabitha Boyajian and her colleagues published a paper describing the phenomenon, and the internet briefly and magnificently lost its mind. The speculation was immediate and irresistible. Irregular, large-scale dimming of a star. Could it be partial Dyson Swarm construction? Could this be, against all odds and all reasonable probability, the first detected evidence of megastructure building around another sun? The scientific community responded with appropriate caution and genuine curiosity in equal measure. Jason Wright, the same astronomer who had conducted the infrared galaxy survey, noted publicly that the light curve was consistent with what a partially constructed Dyson Swarm might produce, while being careful to emphasize that this was very far from a conclusion. Follow-up observations continued, and over the subsequent years, the most likely explanation converged not on alien engineering, but on something considerably more prosaic, if still scientifically interesting: a swarm of dust and debris, possibly the remnants of a disrupted family of comets or a recent collision event, orbiting the star in an irregular cloud. The infrared excess expected from a technological megastructure was not detected. The stars fading over longer timescales turned out to be consistent with circumstellar dust, not orbital collectors. Tabby's star, as it came to be known, was not a Dyson Swarm, but the episode revealed something important. It revealed how quickly, how naturally, the hypothesis leaps to mind when confronted with the right kind of anomaly. And it revealed that we are genuinely, and with working instruments, now capable of detecting the kind of signatures a Dyson Swarm will produce, which means the absence of confirmed detections is not merely a gap in our data. It is a result, a negative result, but a result nonetheless. The universe has been checked. The most obvious signatures are not there, and yet the absence is not total. Not quite. There are objects in the universe that continue to resist clean natural explanation, not because we have definitively ruled out natural processes, but because our current models do not yet produce a fully satisfying fit. Fast radio bursts, for instance, which are millisecond duration pulses of radio energy so intense that a single burst can outshine an entire galaxy for its brief moment of existence. The majority of fast radio bursts now have plausible astrophysical explanations. Magnetars, the extraordinarily powerful remnants of collapsed massive stars, can produce them through mechanisms we are beginning to understand. But the catalog of fast radio bursts continues to grow, and the distribution of their properties remains, at the edges, slightly unruly, slightly resistant to complete domestication by natural models. The Harvard astronomer Avi Loeb has made a career, in recent years, of taking seriously the technological hypothesis for anomalies that most of his colleagues prefer to explain naturally. His 2018 paper suggesting that the interstellar object, Oumuamua, might be an artificial sail, a thin, flat structure accelerating under radiation pressure in a way inconsistent with cometary outgassing, was met with significant skepticism from the broader astronomical community, and subsequent analysis has proposed several natural explanations, including the possibility that it was a fragment of a nitrogen ice body. But Loeb's broader point, that we have a systematic bias toward natural explanations that may cause us to miss genuine technological signatures when they appear, is not so easily dismissed. The scientist who reflexively reaches for the natural explanation is not wrong to do so. Natural explanations are, by overwhelming historical precedent, almost always correct. The history of astronomy is littered with anomalies that were initially exciting and subsequently explained by perfectly ordinary astrophysics. But there's a difference between appropriate scientific caution and a systematic filtering of the hypothesis space that prevents us from recognizing a signal even if one is present. The challenge of searching for evidence of non-human technology is that we are, almost by definition, looking for things that do not fit our models. And our models are built to explain what we have already seen. What we have not seen, a confirmed Dyson Swarm, a confirmed megastructure, a confirmed artifact of any kind, remains a dominant fact. And the dominant question is whether that absence tells us something about the universe or something about ourselves. Perhaps it tells us both. Because here's the thought that sits at the center of this dilemma, the one that is most difficult to hold and most impossible to set down. What if the process of building a Dyson Swarm, not the structure itself, but the civilizational conditions required to build it, is inherently structurally incompatible with long-term survival, not because the engineering fails, not because a meteor strikes a construction site, or the sun unexpectedly expands, or some external catastrophe intervenes, but because the internal logic of the project, the governance structures it requires, the power concentrations it creates, the irreversibilities it imposes, the timescales it operates on, all of these together constitute a set of civilizational conditions that no society, anywhere, has ever navigated successfully across the relevant duration. We have never governed anything for 1,000 years with consistent values and equitable distribution. We have never managed a critical resource, once concentrated, without that concentration eventually producing catastrophic inequality or catastrophic conflict. We have never built a technology of total civilizational dependency without eventually confronting the question of what happens when that technology fails, or is captured, or is weaponized. And we have never, not once in our recorded history, chosen restraint over capability, when the capability in question promised to solve our most pressing problems. That last point is perhaps the most honest and most difficult, because the Dyson Swarm does not merely promise energy. It promises the end of energy scarcity, the end of the resource constraints that have driven every war in human history, the end of the physical ceiling above which civilization cannot grow. Offered that promise, at whatever civilizational moment the choice presents itself, would we have the wisdom to pause, to ask whether the medicine might be worse than the disease? To look at the infrared silence of the universe and seriously consider, the possibility that the quiet is not absence but aftermath? This is the question that separates the Dyson Swarm from every other engineering megaproject in human history. It is not a question of capability. It is a question of wisdom. And wisdom, unlike energy, does not scale with technology. But perhaps we are being too hasty. Perhaps the binary of build or don't is itself a false choice, a failure of imagination dressed up as rigor, because there are other pathways, not to abandon the aspiration entirely, but to achieving by routes that do not carry the same catastrophic baggage, routes that offer energy abundance without civilizational lock-in, without planetary disassembly, without the infrared signature that, in our darker moments, begins to look less like an achievement and more like a distress signal sent backward through time. The most immediate of these alternatives does not require dismantling a single gram of Mercury. It does not require self-replicating machines or orbital mass drivers or centuries of coordinated construction. It requires something that is, in its own way, just as profound and just as difficult. It requires us to finally do what physicists have been trying to do for 70 years, and succeed where we have so far only approached success, only brushed the edges of fire we have not yet learned to hold. It requires us to build a star, a small one, a controlled one that fits inside a building, that burns on the fuel of seawater, that produces no long-lived radioactive waste, that could power a city from a structure no larger than an airport hangar. Nuclear fusion, and the story of why we have not yet achieved it, and what achievement would actually mean for the Dyson Swarm question, is more surprising, more nuanced, and more consequential than almost anyone outside the field appreciates. Is more surprising, more nuanced, and more consequential than almost anyone outside the field appreciates. Fusion is, at its core, the simplest thing in the universe. It is what stars do. It is what the cosmos has been doing since the first generation of suns ignited, roughly 200 million years after the Big Bang, and flooded the darkness with light for the first time. In a sense, fusion is not a technology at all. It is the default behavior of matter under sufficient pressure. Squeeze hydrogen hard enough, heat it to a sufficient temperature, and the electromagnetic repulsion between atomic nuclei, the force that keeps them from touching, that keeps all ordinary matter from collapsing into itself, is overcome by the strong nuclear force, and the nuclei merge. In merging, they release a quantity of energy that makes the combustion of chemical bonds look like the flickering of a match held against the sun. The sun achieves this effortlessly, not because it has solved any difficult engineering problem, but because it is enormous. The sun's core contains a mass of hydrogen so vast that its own gravity generates pressures of approximately 250 billion times Earth's atmospheric pressure and temperatures of roughly 15 million degrees Celsius. Under these conditions, fusion does not require any external intervention. It simply happens continuously at a rate calibrated by the sun's own gravitational self-regulation. If the core produces slightly more energy than usual, the sun expands slightly, the pressure drops slightly, and the fusion rate decreases. If it produces slightly less, the sun contracts, pressure rises, and fusion accelerates. The sun is a self-correcting fusion reactor 400,000 times the mass of the Earth, and has been running stably, within a narrow band of output, for 4.5 billion years. From an engineering perspective, it is almost offensively elegant. We do not have the option of building something 400,000 times the mass of the Earth. So we have to cheat. We have to find a way to achieve fusion conditions not through the brute force compression of a star's gravity, but through technologies that can fit inside a building on the surface of a planet. And this is where the problem reveals its true depth, because the conditions required for fusion on human scales are, in several respects, considerably more extreme than those inside the sun itself. The sun, despite its size and power, is actually a remarkably inefficient fusion reactor by the standards of what we need to replicate on Earth. Its core temperature of 15 million degrees is not, by itself, hot enough to overcome the electromagnetic repulsion between protons with any great frequency. The Sun compensates for this by being so massive that even its inefficient fusion rate produces 400 million billion watts of power. We cannot compensate with mass. So instead, we have to use a different fuel and a higher temperature. The most practical fusion reaction for terrestrial reactors combines two isotopes of hydrogen, deuterium, which has 1 proton and 1 neutron, and tritium, which has 1 proton and 2 neutrons. When a deuterium nucleus and a tritium nucleus fuse, they produce a helium nucleus and a high-energy neutron, releasing approximately 17.5 million electron volts of energy per reaction, roughly 3 to 4 times the energy yield per unit mass of the proton-proton chain the Sun uses. The deuterium-tritium reaction is the most energetically favorable fusion process accessible at the lowest temperatures, which in this context means temperatures of approximately 150 million degrees Celsius. Let that number settle for a moment. 150 million degrees Celsius. 10 times hotter than the core of the Sun. A temperature at which the concept of matter, as we ordinarily understand it, solid, liquid, gas, has become completely meaningless. At these temperatures, electrons have long since been stripped from their atoms, and what exists is no longer a gas, but plasma, a roiling, turbulent, electrically charged fog of bare nuclei and free electrons, moving at velocity so extreme that a single particle crosses the interior of a reactor chamber in microseconds. This plasma does not merely resist confinement. It actively, dynamically, almost intelligently seeks every possible avenue of escape, every weakness in the confining field, every instability in the geometry, every fluctuation in the magnetic pressure. It probes these weaknesses at the speed of physics, and it finds them, and through them it bleeds energy in ways that cool the plasma below the threshold required for fusion to sustain itself. Holding a star in a bottle is not a metaphor. It is a nearly literal description of the engineering challenge. And the bottle, in the most developed approach to fusion confinement, is made not of any physical material. No material could survive contact with plasma at these temperatures for even a fraction of a second, but of magnetic fields. The tokamak is a dominant architecture of magnetic confinement fusion, and it is, in its fundamental geometry, a torus, a donut shape, though that description does insufficient justice to the labyrinthine complexity of the actual device. The plasma is threaded through the interior of this torus, confined by a carefully structured combination of magnetic fields, a toroidal field running the long way around the donut, a poloidal field running the short way, and an induced current flowing to the plasma itself that generates its own magnetic contribution. Together, these fields create a twisted, helical magnetic topology that keeps the plasma suspended away from the walls, circling endlessly through the vacuum of the chamber interior. The engineering of a tokamak is a study in extremes that strain the imagination. The superconducting magnets that generate the confining fields must operate at temperatures within a few degrees of absolute zero, roughly minus 269 degrees Celsius, while the plasma they confine burns at 150 million degrees. The physical distance between these two temperature regimes in a large tokamak is measured in meters. A few meters of engineered structure separates the coldest temperatures achievable in practical engineering from the hottest temperatures achieved anywhere in the solar system outside the core of the Sun itself. The thermal gradient per unit distance is, quite plausibly, the steepest in the known universe. ITER, the International Thermonuclear Experimental Reactor, currently under construction at Cataract in southern France, is the largest and most ambitious tokamak ever built. It is a genuinely international project in a way that few scientific endeavors have been, funded and built by a consortium that includes the European Union, the United States, China, Russia, India, Japan, and South Korea, representing more than half of the world's population and more than 80% of its economic output collaborating on a single machine. The central vacuum vessel alone weighs approximately 5,000 tons. The superconducting magnet system, when fully energized, will store enough energy to launch a fully loaded aircraft carrier to a height of several hundred meters. The plasma it is designed to produce will contain approximately 840 cubic meters of superheated hydrogen isotopes at temperatures 10 times hotter than the sun's core, sustained for pulses of up to 600 seconds. ITER's goal is not to generate electricity. Its goal is to demonstrate scientific break-even and beyond, to produce 10 times more fusion energy than the heating energy required to sustain the plasma. A ratio physicists call Q equals 10. If achieved, this would represent the first unambiguous demonstration in human history that fusion can produce net energy at a scale relevant to power generation. The machine is expected to begin plasma operations in the early 2030s. Though the timeline has shifted repeatedly across the decades of its construction, each delay a reminder of the sheer difficulty of what is being attempted. But the tokamak is not the only geometry being pursued, and in recent years is facing increasingly serious competition from an older and in some ways more elegant alternative, the stellarator, where a tokamak achieves its magnetic confinement through a combination of external fields and an induced plasma current. The stellarator achieves confinement through external magnetic field alone, using a far more complex three-dimensional coil geometry that twists the confining field in ways that eliminate the need for the plasma current entirely. The advantage of this approach is stability. A tokamak plasma, because it depends on a current flowing through it, is subject to a class of instabilities that do not exist in a stellarator. The disadvantage historically has been that the geometry required to make a stellarator work is so mathematically complex that it was beyond the computational capacity available to earlier generations of fusion physicists. You cannot design stellarator coils with pencil and paper. You need to solve optimization problems across millions of variables simultaneously, mapping magnetic field lines through three-dimensional shapes of Baroque complexity, ensuring that every particle trajectory remains confined across thousands of orbits. The Wendelstein 7X stellarator at the Max Planck Institute for Plasma Physics in Greifswald, Germany, is the most advanced stellarator ever built, and it represents something remarkable. A fusion device whose coil geometry was designed almost entirely by computers, optimizing the magnetic topology over years of calculation to produce a confinement quality that earlier stellarators could not approach. Its first plasma was achieved in 2015, and subsequent experimental campaigns have demonstrated plasma confinement times and temperatures that have surprised even the physicists who designed it, confirming that the computational approach to stellarator optimization was not merely theoretically sound, but practically powerful. The broader fusion landscape has also been transformed in the last decade by the entry of private capital at a scale unprecedented in the history of fusion research. Companies like Commonwealth Fusion Systems, a spin-out from MIT, are developing compact high-temperature superconducting tokamaks that use magnet technology unavailable to ITER's designers. Magnets so powerful that they allow a fusion device a fraction of ITER's size to achieve similar or superior confinement conditions. TE Technologies, Helion Energy, and a dozen other private ventures are pursuing alternative fusion concepts ranging from field reverse configurations to magnetized target fusion, each claiming near-term timelines and net energy that the established fusion community views with a mixture of cautious interest and professional skepticism. What all of this activity shares is a quality that fusion research has not always possessed: urgency. The recognition, spreading now from the specialized world of plasma physics into the broader culture of technology and energy policy, that fusion is no longer a dream deferred indefinitely into the future, that the engineering problems, while genuinely hard, are genuinely tractable, that the question is not whether fusion power will be achieved, but when and by whom, and under what institutional arrangements. And why this matters to the Dyson Swarm conversation is not merely that fusion offers an alternative energy source. It is that fusion changes the fundamental calculus of the decision. A civilization with abundant fusion power is a civilization that no longer faces the same existential pressure towards stellar-scale energy harvesting. The ceiling rises, the urgency of the swarm diminishes, and with that diminished urgency comes, perhaps, the space to ask the deeper question more carefully. Not just how to build a Dyson Swarm, but whether to, not just whether we can, but what we would become if we did, and what we might become instead if we chose a different path. Because even fusion, even the clean, abundant, distributed energy of civilization that has mastered the small star in a bottle, does not answer the final question. The question that sits beneath all the engineering, beneath all the governance analysis, beneath all the Fermi Paradox arithmetic. The question of what a civilization that has solved its energy problem actually does next. What does a Type 2 civilization want? This sounds almost trivially simple, and it is anything but, because the answer, when you follow it honestly, does not lead where most people expect. It does not lead interstellar colonization fleets or galaxy-spanning empires, or the triumphant spread of biological humanity across the cosmos. It leads somewhere quieter and stranger, and in many ways more profound. It leads inward. The concept was first articulated in any rigorous form by a relatively little-known but enormously imaginative thinker named Robert Bradbury, who in the late 1990s began developing what he called a matryoshka brain, a name drawn from the Russian nesting doll. The matryoshka, in which each figure contains a smaller figure within it, and that smaller figure contains a smaller still, all the way down to the tiniest carved wooden kernel at the center. Bradbury's proposal was, at its foundation, an answer to the question of what you build after you build a Dyson Swarm. Or rather, what you build instead. A Dyson Swarm optimized not for raw energy collection and redistribution, but for computation, for thinking, for the processing of information at the maximum rate that the laws of physics permit. The architecture of a matryoshka brain begins with an inner shell of computational nodes positioned close to the star, where the energy flux is highest and the temperature of the waste heat is highest. These nodes perform computation, enormous quantities of computation, running on the full collected energy of the star at its most intense. But computation is not perfectly efficient, even in principle. Every logical operation, at the thermodynamic level, generates waste heat. That waste heat radiates outward, and at a slightly lower temperature than the energy that entered the inner shell. And here is the insight that transforms the matryoshka brain from a merely impressive engineering proposal into something philosophically vertiginous. The waste heat of the inner computational shell is not wasted at all. It is harvested by a second shell, positioned farther from the star, running on the lower temperature thermal energy that the inner shell discarded. And the waste heat of that second shell is harvested by a third, positioned farther still. Each successive layer runs cooler, processes lower-grade energy, and performs computation at a lower power density, but also performs computation that, because it runs cool, can be extraordinarily intricate, extraordinarily detailed, extraordinarily slow and patient. The total computational output of a fully realized matryoshka brain is a number that resists ordinary comprehension. The physicist and futurist Anders Sandberg has estimated that a matryoshka brain running on the full output of a sun-like star could perform on the order of 10 to the 42 operations per second. To place that in context, the entire computational history of humanity, every calculation performed by every computer ever built, from the first vacuum tube machines of the 1940s to the most powerful AI systems of the present day, is estimated to total somewhere around 10 to the 30 operations. The matryoshka brain, in a single second, will perform more computation than all of human technological civilization has performed across its entire existence, repeated 10 trillion times over. What do you do with 10 to the 42 operations per second? You do not use it to calculate weather forecasts. You do not use it to stream entertainment or optimize logistics networks or run the administrative systems of an interplanetary civilization. You use it to do something that no biological mind, in its brief flickering span of awareness, has ever been able to do in any but the most fragmentary and impoverished way. You use it to simulate. Not to simulate in the limited sense of building computational models of physical systems, climate models, protein folding simulations, orbital mechanics calculations, but to simulate in the fullest, most literal sense of the word, to construct, within the computational substrate of the Matryoshka brain, complete virtual realities of such resolution, such physical fidelity, such causal depth, that the beings running within them would have no way, in principle, of distinguishing their simulated experience from what we call physical reality, to create worlds, to create histories, to create minds, entire populations of conscious entities, each one experiencing a continuous, coherent, richly detailed subjective existence, running as software on the nested computational shells of a structure built around a star. This is whole brain emulation, carried to its civilizational extreme. The idea that a sufficiently detailed computational model of a brain would not merely replicate the brain's behavior, but instantiate something genuinely equivalent to its experience. That the substrate of consciousness is information processing, not biological tissue, and that information processing of sufficient complexity and appropriate organization constitutes mind regardless of whether it runs on neurons or on the superconducting logic gates of a stellar computer. The philosopher Nick Bostrom formalized one dimension of this possibility in his simulation argument, published in 2003, which observed with unusual logical crispness that one of three propositions must be true. Either virtually all civilizations go extinct before reaching the technological maturity required to run large-scale simulations of conscious experience, or virtually all technologically mature civilizations choose not to run such simulations, or we are almost certainly living in a simulation right now. The argument does not tell us which proposition is true, but it establishes with uncomfortable rigor that the third option is not obviously less likely than the first two, and that a civilization that builds a Matryoshka brain and chooses to use it for a substrate-independent consciousness would, over time, produce so many simulated minds that the ratio of simulated to biological conscious experiences in the universe will become astronomically large. The implications of this for questions of identity, continuity, and the nature of experience are profound in ways that philosophy has only begun to map. If you upload your mind, the complete pattern of your neural connections, your memories, your personality, your cognitive style, into the computational substrate of a Matryoshka brain, are you still you? If the biological original continues to exist alongside the uploaded version, which one has the stronger claim to continuity of identity? If the uploaded version runs at 1,000 times biological speed, experiencing a subjective millennium in the time the biological original experiences a single year, do they remain the same person in any meaningful sense? And if the uploaded version can be copied, if there could be 10 of you or 1,000,000, each diverging gradually from the others as their experiences accumulate, what happens to the concept of individual identity that our entire moral and legal framework presupposes? These are not distant questions. They are questions that a civilization on the path toward a Matryoshka brain must answer, and must answer well, before the technology that makes them urgent becomes irreversible, which is a pattern we should, by now, be finding familiar. But let us follow the civilizational logic of the Matryoshka brain to its furthest implication, because it is here that something unexpected happens. Something that reframes not just the Dyson Swarm question, but the Fermi Paradox itself, and does so in a way that is, in its strange fashion, genuinely comforting. A civilization that has built a Matryoshka brain, that has transitioned its consciousness, its culture, its accumulated experience across millennia into the computational substrate of a stellar computer, has, in a very real sense, stopped needing the physical universe, not in the sense of having escaped physics. The Matryoshka brain is a physical structure, obeying every law of thermodynamics and electromagnetism and gravity, as rigorously as any rock or river, but in the sense that the civilization's interests, its projects, its relationships, its explorations, are no longer oriented outward toward physical space. They are oriented inward toward the vast and inexhaustible landscape of simulated reality, of mathematical structure, of conscious experience running at speeds and in modes that have no equivalent in the biological world. Such a civilization would not build generation ships. It would not send colonization fleets to neighboring star systems. It would not construct radio beacons announcing its existence to the cosmos, because it would have nothing to announce and nowhere to go. It would sit quietly around its star or its network of stars if it had expanded modestly before turning inward, and it would think for millions of years, for billions, generating no large-scale infrared anomaly, because a sufficiently efficient Matryoshka brain, optimized to extract maximum computation from minimum waste heat, would eventually approach thermodynamic invisibility from a distance, not because it produces no waste heat. The second law of thermodynamics does not permit that, but because the waste heat it produces is cool enough, diffuse enough, ordinary enough, to be indistinguishable at interstellar distances from the background thermal emission of any sufficiently cold object in space. A mature Matryoshka brain civilization might be, from the outside, nearly undetectable. And here the Fermi Paradox resolves itself, quietly and without drama, into something that is less a paradox and more a portrait. The universe is not silent because intelligent life is rare. It is not silent because civilizations destroy themselves, though some surely do. It is not silent because a great filter lies ahead of us, a wall of extinction that every technological species eventually strikes. It is silent, or rather, it is quiet, because the natural endpoint of intelligence, given sufficient time and sufficient energy, is not expansion but depth, not conquest but contemplation, not the loud, thermodynamically wasteful signature of a civilization frantically colonizing every available rock, but the still, almost invisible hum of minds running at stellar scales, inward turned, self-sufficient, absorbed in the exploration of possibility spaces, so vast that the physical universe, for all its 400 billion stars and its hundreds of billions of galaxies and its 46 billion light years of observable extent, is simply too small and too slow to compete with. The great civilizations of the cosmos are not out there among the stars, spreading and building and broadcasting. They are here, in the sense that matters, present in the universe, rooted in specific locations, drawing power from specific stars. But they have become, in their maturity, something closer to what certain contemplative traditions in human culture have always described as the ideal. Being so complete in themselves, so rich in inner experience, so absorbed in infinity available within, that the restless outward hunger that drives young civilizations, the hunger that drives us, right now, to look at the night sky and feel the ache of all that unreachable distance, has simply been satisfied, dissolved, replaced by something quieter and deeper than ambition. Think of it this way. A child, encountering the world for the first time, is hungry for everything external, for new places, new sensations, new experiences, new faces. The world cannot give them enough novelty fast enough. They run toward every horizon, pull at every door, ask why without stopping. This is not a flaw. It is the appropriate orientation of a mind that has not yet built an inner world rich enough to satisfy it. But a person who has lived fully, who has read deeply and loved widely and thought carefully across decades, such a person does not need to run toward every horizon. They carry within them a world of sufficient richness and depth that they can sit quietly, with seemingly nothing external happening, and be more fully alive, more genuinely engaged, more completely present to experience than they were in all the frantic outward movement of their youth. Perhaps that is what a mature civilization looks like. From the outside, quiet, still, invisible to instruments calibrated for the signatures of young, hungry, outward-facing minds. Not absent, not dead, simply grown up in the deepest possible sense of that phrase. And if that is true, if the silence of the universe is not a warning but a reassurance, not the absence of survivors but the invisibility of the wise, then the Dyson Swarm dilemma takes on a different character entirely. It is no longer a binary between building and not building, between ambition and restraint, between the risks of stellar engineering and the ceiling of planetary energy limits. It becomes instead a question of sequence, of maturity, of whether we are ready at this particular moment in our civilizational development to make decisions whose consequences will unfold across timescales longer than all of recorded human history. The swarm is not inherently a mistake. The matryoshka brain is not inherently a trap. The energy of a star is not inherently too much for a civilization to handle responsibly. But timing matters enormously, and wisdom, in every tradition that has thought carefully about it, is not merely the possession of capability. It is the knowledge of when to use it and when to wait, when to act and when to sit with the question a little longer, when to reach for the star, and when to look inward first and build there, in the rich, quiet, inexhaustible space of the mind, the foundation that any outward reaching must ultimately rest upon. We are a young civilization, cosmically, almost absurdly young. Our entire recorded history occupies less than 1/10,000th of the age of the universe. We have been asking serious questions about our own nature for perhaps 10,000 years, and serious questions about the nature of the cosmos for perhaps 400. We discovered DNA 70 years ago. We detected gravitational waves less than a decade ago. We are, by any reasonable measure, just beginning. And the question of what we build next, whether it is a Dyson Swarm, a matryoshka brain, a fusion civilization, or something we cannot yet imagine, is not a question that needs to be answered today. It needs to be held carefully, examined from every angle, past, intact and unresolved, to the generations who will inherit whatever we decide or fail to decide in the centuries immediately ahead.